Hello there, and welcome to the Sleepy Science Society. Tonight, we're drifting into the quiet depths of space, where ancient light still travels, where stars burn with a fierce and silent beauty, and where the story of everything we know begins. If you find yourself relaxing into these gentle explorations of the cosmos, I invite you to like, subscribe, or share a thought below. It helps other curious souls discover this peaceful corner of the universe, one sleepy mind at a time. But for now, all you need to do is settle in, let your shoulders drop, allow your breathing to slow. And let's begin our journey through the stars. When you look up at the night sky on a clear evening, far from the glow of city lights, you see something that has captivated humanity for all of recorded history. Scattered across the darkness like diamond dust on black velvet, thousands of points of light shimmer and pulse. Some burn with a steady, cool blue-white glow. Others flicker with warmer, reddish hues. A few shine so brightly they seem to pierce through the atmosphere itself, while countless more huddle together in faint, ghostly bands that stretch from horizon to horizon. These are stars, and each one of them is a sun. For our ancestors, stars were navigational beacons, seasonal calendars, and the subjects of myths that tried to explain the unexplainable. Ancient Polynesians crossed vast stretches of empty ocean by reading the positions of stars with extraordinary precision. Desert travelers oriented themselves by the North Star, which has remained relatively fixed in the sky for thousands of years as Earth spins beneath it. Farmers watched the rising and setting of particular constellations to know when to plant their crops and when to harvest. In nearly every culture that has ever existed, humans have looked at stars and seen patterns, stories, gods, and ancestors. But stars are far more than points of light in our night sky. They are massive nuclear furnaces, each one a seething sphere of plasma where temperatures reach millions of degrees at the core. They are the crucibles where nearly every element heavier than hydrogen was forged. The carbon in your cells, the calcium in your bones, the iron in your blood, all of it was created inside the burning hearts of stars that lived and died long before our solar system even existed. When you look at stars, you are seeing your cosmic ancestry written across the heavens. The story of stars begins in darkness. In the vast spaces between existing stars, enormous clouds of gas and dust drift through the void. These clouds, called the molecular clouds or stellar nurseries, can be hundreds of light years across and contain enough material to birth thousands or even millions of new stars. They are cold, just a few degrees above absolute zero, and so dark that visible light cannot penetrate them. Inside these clouds, matter is not evenly distributed. Here and there, pockets of gas are slightly denser than their surroundings, and in those denser regions, something remarkable begins. Gravity, that patient and inexorable force, begins to pull. Atoms of hydrogen and helium, along with microscopic grains of dust, start to drift toward the center of these dense pockets. As more matter accumulates, the gravitational pull grows stronger, drawing in even more material from the surrounding cloud. This process feeds on itself. The more mass that gathers, the stronger gravity becomes, and the faster new material falls inward. What began as a barely perceptible increase in density becomes a runaway collapse. As the cloud collapses, something interesting happens. The infalling material doesn't have a perfectly straight path toward the center. Some of it has sideways motion, angular momentum that causes the whole collapsing region to begin spinning. As it spins faster, it flattens into a disk, much like pizza dough spinning in the air. At the very center of this rotating disk, where matter is falling in from all directions, a hot, dense core begins to form. This is a protostar, the embryonic stage of a star's life. A protostar doesn't yet shine with its own nuclear fire. The light and heat it produces come from gravitational energy, from the simple act of matter falling inward and converting its potential energy into heat. But that heat is not insignificant. As more and more material crashes down onto the growing protostar, temperatures at the core climb, hundreds of thousands of degrees, then millions. The pressure becomes immense, with billions of tons of gas pressing down from all sides. The protostar glows in infrared wavelengths, invisible to human eyes but detectable by specialized telescopes that can peer through the dusty clouds surrounding it. This phase can last anywhere from 100,000 years to several million years, depending on how massive the protostar becomes. During this time, the disk of material surrounding the young star begins to change. Some of it continues to fall onto the star itself, feeding its growth. Other portions of the disk start to clump together, forming the seeds of what might one day become planets. Jets of material, driven by complex magnetic fields, shoot out from the star's poles, piercing through the surrounding cloud and making the star's presence known even through layers of obscuring dust. Eventually, if the protostar accumulates enough mass, a threshold is reached. Deep in the core, where temperatures have climbed to around 15 million degrees Celsius, hydrogen nuclei begin to move so fast that they can overcome the electrical repulsion that normally keeps them apart. When two hydrogen nuclei collide with enough energy, they fuse together to form helium, releasing a tremendous burst of energy in the process. This is nuclear fusion, the same process that powers hydrogen bombs, but here it is controlled and sustained by the immense gravitational pressure of the star itself. Once nuclear fusion ignites, the star enters the main sequence phase of its life. A main sequence star is in a state of near perfect balance. The outward pressure from nuclear fusion in the core pushes against the inward pull of gravity, creating a stable equilibrium that can last for millions, billions, or even trillions of years. This is by far the longest phase of any star's existence. Our own Sun, for instance, has been a main sequence star for about 4.5 billion years, and it will continue to shine in much the same way for another 5 billion years before significant changes begin. Not all stars are created equal. The mass of a star determines nearly everything about its life, from how brightly it shines to how long it will live. The smallest stars that can sustain nuclear fusion are red dwarfs, with masses as low as about 8% that of the Sun. These tiny stars burn their fuel so slowly and so efficiently that they can remain on the main sequence for trillions of years, far longer than the current age of the universe. Some red dwarfs that formed soon after the Big Bang are still in their infancy by stellar standards, having used only a fraction of their hydrogen fuel. At the other end of the spectrum are massive stars with tens or even hundreds of times the mass of the Sun. These stellar giants burn with incredible ferocity. Their cores are so hot and their fusion rates so high that they blaze through their fuel in mere millions of years. A star with 50 times the Sun's mass might live for only 3 or 4 million years before it exhausts its hydrogen supply, a cosmic blink compared to the slow burn of a red dwarf. The color of a star tells you about its temperature. The coolest stars glow with a deep red color, their surface temperatures hovering around 3,000 degrees Celsius. These are the red dwarfs and red giants, stars that radiate most of their energy in the infrared part of the spectrum. Yellow stars, like our Sun, have surface temperatures of around 5,500 degrees and emit light across the visible spectrum in a fairly balanced way, which is why sunlight appears white when all its colors are combined. Moving up the temperature scale, we find white stars at around 10,000 degrees. And finally, the hottest stars of all, the blue giants and supergiants, which can have surface temperatures exceeding 30,000 degrees Celsius. These stars pour out enormous amounts of ultraviolet radiation and appear blue-white to our eyes. During the main sequence phase, a star is essentially in a holding pattern. Hydrogen fuses into helium in the core. Energy radiates outward through the star's layers, and the star maintains a consistent size, temperature, and luminosity. For a star like the Sun, this phase represents about 90% of its entire lifetime. The star doesn't change much during these billions of years, at least not in ways that would be obvious over human timescales. But the fusion process is slowly changing the composition of the core. With every second that passes, millions of tons of hydrogen are converted into helium, and the core gradually becomes helium-rich, while the surrounding layers remain mostly hydrogen. This gradual change sets the stage for what comes next. Because helium atoms are heavier than hydrogen atoms, they settle toward the center of the star. As the core becomes more helium-rich and hydrogen-poor, the rate of fusion in the very center begins to slow. But fusion continues in a shell around the helium core, and something interesting happens. The energy output from this shell fusion actually increases, causing the outer layers of the star to expand. The star grows larger, its surface moves farther from the core, and as a result, the surface cools and reddens. The star is becoming a red giant. For stars like our Sun, with masses between about half a solar mass and 8 solar masses, the red giant phase is a slow but dramatic transformation. Over the course of several million years, the star swells to enormous proportions. The Sun, when it eventually becomes a red giant, will expand beyond the orbit of Mercury, possibly even reaching Venus or Earth. Its surface will glow with a deep orange-red color. And even though each square meter of that surface will be cooler than it is now, the total surface area will be so vast that the star will shine far more brightly than it does today. Inside the red giant, interesting things are happening in the core. That ball of helium that has been building up is growing denser and hotter under the pressure of the layers above. Eventually, temperatures in the core reach around 100 million degrees Celsius, hot enough for a new type of fusion to begin. Helium nuclei, also called alpha particles, start to fuse together. 3 helium nuclei combine to form carbon in a process called the triple alpha process. As helium fusion proceeds, some of the carbon can fuse with additional helium to create oxygen. The star now has a core producing carbon and oxygen, surrounded by a shell where hydrogen is still fusing into helium. This pattern of shells within shells is characteristic of evolved stars. As one type of fuel runs out in the core, fusion ignites in a shell around it. And if the star is massive enough, a new type of fusion can eventually begin in the core itself. For stars like the Sun, the process stops at carbon and oxygen. The core never gets hot enough to fuse these heavier elements. Instead, after a few million years of helium fusion, the star becomes unstable. Vast amounts of the star's outer envelope are blown away in gentle but persistent stellar winds, forming beautiful structures called planetary nebulae. Planetary nebulae are among the most visually stunning objects in the universe. They glow with vibrant colors: reds from hydrogen, greens, and blues from oxygen, often forming intricate shapes like rings, hourglass figures, or butterfly wings. These shapes are sculpted by complex interactions between the star's stellar winds, magnetic fields, and sometimes the influence of companion stars. The material blown off in this phase contains not just hydrogen and helium, but also the carbon and oxygen created in the star's core, along with trace amounts of heavier elements. This enriched material spreads into the interstellar medium, where it can eventually be incorporated into new generations of stars and planets. At the center of the planetary nebula, the core of the old star remains. This core is no longer capable of fusion. It's a ball of carbon and oxygen, incredibly dense, about the size of Earth, but containing roughly half the mass of the Sun. This is a white dwarf. White dwarfs are supported not by fusion, but by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being squeezed any closer together. A white dwarf is extremely hot when it first forms, with surface temperatures that can exceed 100,000 degrees Celsius. It glows white hot, hence the name. But a white dwarf is a dying ember. With no fusion to replenish its energy, it can only cool and fade. Over billions of years, a white dwarf will radiate away its heat, gradually shifting from white to yellow to red, and eventually to a cold, dark cinder called a black dwarf. However, the universe is not yet old enough for any black dwarfs to exist. Even the oldest white dwarfs, formed shortly after the first stars in the universe, are still glowing faintly. They will continue to cool for many trillions of years before they finally fade completely. The fate of more massive stars is far more dramatic. Stars with more than about 8 times the mass of the Sun have enough gravity to push fusion beyond carbon and oxygen. When such a star exhausts its hydrogen, it becomes a red supergiant, even larger than a red giant. The star Betelgeuse visible as the reddish shoulder of Orion, is a red supergiant. If placed at the center of our solar system, Betelgeuse would extend past the orbit of Mars, engulfing the inner planets entirely. Inside a massive star, fusion proceeds through a series of stages, each one building heavier elements. After helium fuses into carbon and oxygen, the core contracts and heats up again until carbon fusion can begin, producing neon, sodium, and magnesium. When carbon is exhausted, neon fusion ignites, creating oxygen and magnesium. Then, oxygen fusion produces silicon and sulfur. Finally, silicon fusion creates iron. Each stage releases less energy than the one before, and each stage lasts for a shorter time. A massive star might spend millions of years fusing hydrogen, hundreds of thousands of years fusing helium, a few hundred years fusing carbon, and just 1 year fusing silicon. Iron is the end of the line. Unlike all the lighter elements, fusing iron doesn't release energy. It requires energy. When a massive star builds up an iron core, nuclear fusion can no longer support the star against gravity. The core grows until it reaches a critical mass, about 1.4 times the mass of the Sun, compressed into a sphere not much larger than Earth. At that point, the core can no longer support itself. In a fraction of a second, the core collapses. What happens next is one of the most violent events in the universe. As the iron core collapses, it doesn't stop at white dwarf density. It keeps collapsing, reaching densities comparable to an atomic nucleus. Protons and electrons are squeezed together so hard that they merge into neutrons. The core becomes a ball of neutrons just 20 kilometers across, a neutron star, and the collapse halts with stunning abruptness as neutron degeneracy pressure finally provides enough support to resist further compression. The outer layers of the star, which have been falling inward during the core collapse, suddenly slam into this incredibly hard, incompressible neutron core. The impact, combined with a flood of neutrinos bursting out from the core, creates a shock wave that blasts back outward through the star. This shock wave tears the star apart in a supernova explosion, one of the brightest events in the cosmos. For a few weeks, a single supernova can outshine an entire galaxy of hundreds of billions of stars. Supernovae are not just spectacular. They are essential. During the explosion, the extreme conditions of temperature, pressure, and neutron flux allow fusion reactions that would never occur in a stable star. Elements heavier than iron, things like gold, silver, platinum, and uranium, are created in these final moments and scattered into space. Without supernovae, the universe would contain only hydrogen, helium, and trace amounts of lithium from the Big Bang. Every other element, every atom that makes up planets and life and technology, was forged inside stars and dispersed by supernova explosions. After the supernova fades, a remnant is left behind. If the original star's core was between about 1.4 and 3 times the mass of the Sun, what remains is a neutron star. Neutron stars are among the strangest objects in the universe. A typical neutron star contains about 1.5 times the mass of the Sun compressed into a sphere just 20 kilometers in diameter, about the size of a city. To put that density in perspective, A sugar cube-sized piece of neutron star material would weigh about 1 billion tons on Earth. The gravitational pull on the surface of a neutron star is about 100 billion times stronger than Earth's gravity. If you could somehow stand on a neutron star, you would be instantly crushed into a layer of atoms just a few atoms thick. Neutron stars don't just sit quietly in space. Many of them are pulsars, rapidly rotating neutron stars with powerful magnetic fields. When a massive star collapses into a neutron star, conservation of angular momentum causes the neutron star to spin incredibly fast. A star that took a month to rotate once might, after collapsing, spin hundreds of times per second. The fastest known pulsar rotates 716 times per second. Imagine a sphere with the mass of the Sun, 20 kilometers wide, spinning around more than 700 times every single second. The magnetic field of a pulsar is equally extreme. Before collapse, a star might have a magnetic field similar to the Sun's, which is already thousands of times stronger than Earth's magnetic field. When the star collapses, magnetic flux is conserved, and the field lines are squeezed together. The result is a magnetic field trillions of times stronger than Earth's. This intense magnetic field channels charged particles from the neutron star's surface into narrow beams that shoot out from the magnetic poles. As the neutron star spins, these beams sweep through space like lighthouse beams. If Earth happens to lie in the path of one of these beams, we detect a pulse of radiation each time the beam sweeps past. This is how pulsars got their name. The discovery of pulsars is one of the great stories of modern astronomy. In 1967, a graduate student named Jocelyn Bell was using a newly constructed radio telescope to study how radio waves from distant objects twinkled as they passed through the solar wind. While analyzing miles of paper chart recordings, she noticed something odd. There was a signal that appeared at regular intervals, pulsing with extraordinary precision every 1.3 seconds. The signal was so regular that Bell and her advisor, Anthony Hewish, briefly considered whether it might be artificial, possibly a signal from an extraterrestrial civilization. They jokingly labeled it LGM for Little Green Men. But further observations revealed more pulsing sources in other parts of the sky, each with its own precise period. It became clear that these were not artificial signals but natural objects, and the connection to neutron stars was quickly made. The regularity of the pulses could only be explained by a rotating object, and only something as compact and massive as a neutron star could rotate so quickly without tearing itself apart. Later, a pulsar was discovered at the center of the Crab Nebula, the remnant of a supernova that was observed by Chinese astronomers in the year 1054. This pulsar spins 30 times per second and emits pulses not just in radio waves, but also in visible light and X-rays. Its discovery confirmed that pulsars are indeed rotating neutron stars. Not all pulsars spin at the same rate. Young pulsars, freshly formed from supernova remnants, tend to spin relatively slowly, perhaps once per second or a few times per second. Over millions of years, these pulsars gradually slow down as they lose energy through their powerful magnetic fields and particle winds. Eventually, they slow down so much that they can no longer produce detectable pulses, entering what astronomers call the pulsar graveyard. But some pulsars get a second lease on life. If a neutron star exists in a binary system with another star, it can pull material off its companion. This infalling material carries angular momentum, and as it spirals down onto the neutron star, it spins the neutron star up, faster and faster, like a cosmic merry-go-round. These recycled pulsars can end up rotating hundreds of times per second, earning them the name millisecond pulsars. Despite their incredible spin rates, millisecond pulsars are among the most stable clocks in the universe. Their rotation periods are so consistent that they can be used to test fundamental physics, including the detection of gravitational waves from distant colliding black holes and neutron stars. Some neutron stars are even more extreme than typical pulsars. These are magnetars, neutron stars with magnetic fields 1,000 times stronger than those of ordinary neutron stars. Where a typical pulsar might have a magnetic field of 1,000,000,000,000 Gauss, a magnetar's field can reach 1,000,000,000,000 Gauss or more. To put this in perspective, any atomic structure would be torn apart by fields just 1/10 this strong. The magnetic field of a magnetar is so intense that it can actually warp the fabric of space-time around it. Magnetars are temperamental objects. The crust of a neutron star is locked to its magnetic field, and as the field evolves and shifts, it can crack the crust in what's called a starquake. When this happens, the magnetic field lines snap and reconnect, releasing tremendous bursts of X-rays and gamma rays. These flares can be detected across vast distances. In 2004, a magnetar located 50,000 light-years away released a flare so powerful that it briefly affected Earth's upper atmosphere, despite the enormous distance. If that same flare had occurred within 10 light-years of Earth, it would have caused a mass extinction. For the most massive stars, even a neutron star isn't the final state. If the core of the collapsing star has more than about 3 solar masses, neutron degeneracy pressure isn't enough to stop the collapse. Nothing can stop it. The core continues to collapse past neutron star density, and according to general relativity, it keeps collapsing forever, or at least until it reaches a singularity, a point of infinite density where the laws of physics as we understand them break down. Around this singularity forms an event horizon, a boundary in space-time beyond which nothing, not even light, can escape. This is a black hole. Black holes are among the most enigmatic objects in astrophysics. They cannot be seen directly because they emit no light, but their presence can be detected through their gravitational influence on nearby matter. If a black hole exists in a binary system with a normal star, it can pull gas off the companion. This gas forms an accretion disk around the black hole, and as it spirals inward, it heats up to millions of degrees, emitting intense X-rays before crossing the event horizon and disappearing forever. Many stellar mass black holes have been discovered this way through their halo X-ray signatures. The event horizon of a stellar mass black hole is not large. For a black hole with 3 times the mass of the Sun, the event horizon has a radius of just 9 kilometers. But this small region contains all the mass that once belonged to a massive star, compressed into a volume smaller than a city. The gravitational pull near a black hole is so strong that time itself slows down relative to distant observers. An astronaut falling toward a black hole would seem, from a safe distance, to slow down and freeze at the event horizon, their image becoming increasingly red-shifted and dimmer, never quite crossing over. But from the astronaut's perspective, they would cross the event horizon in a finite time, and once inside, their fate would be sealed. They would be pulled inexorably toward the singularity at the center. Many stars don't live their lives in isolation. In fact, more than half of all stars exist in binary systems or multiple star systems. Binary stars orbit a common center of mass, held together by gravity. These systems can be quite varied. Some binaries consist of two main sequence stars that orbit each other at great distances, taking centuries to complete one orbit. Others are so close that they orbit in just hours or days, with their surfaces nearly touching. Binary systems can lead to fascinating interactions, especially as the stars age. If one star becomes a red giant or supergiant, while the other is still on the main sequence, the expanding star can overflow its gravitational boundary, called the Roche lobe, and material can flow from one star to the other. This mass transfer can dramatically alter the evolution of both stars. The donor star loses mass and may never become as bright or as evolved as it would have in isolation. The receiving star gains mass and may be spun up to rotate faster. When a white dwarf exists in a binary system and accretes material from a companion, the consequences can be explosive. Hydrogen from the companion accumulates on the surface of the white dwarf. The white dwarf's intense gravity compresses this hydrogen layer, heating it until it reaches fusion temperatures. When fusion ignites, it does so suddenly and violently in a runaway explosion called a nova. The nova doesn't destroy the white dwarf. It simply blows off the accumulated hydrogen layer in a bright flash. Over time, the white dwarf can accumulate more material and undergo another nova explosion. Some stars have been observed to undergo multiple novae over the course of decades. If a white dwarf accretes enough mass from its companion to push its total mass over the Chandrasekhar limit of about 1.4 solar masses, something even more dramatic happens. The white dwarf can no longer support itself against gravity. It collapses, and the collapse triggers runaway carbon fusion throughout the entire star. The white dwarf detonates in a type Ia supernova, completely destroying itself in the process. Type Ia supernovae are extraordinarily important to astronomy because they always explode at about the same mass. They produce roughly the same peak brightness. This makes them standard candles, objects whose true brightness is known, allowing astronomers to measure distances across the universe. Binary systems involving neutron stars are equally interesting. When two neutron stars orbit each other, they emit gravitational waves, ripples in spacetime predicted by Einstein's general relativity. These gravitational waves carry energy away from the system, causing the orbit to gradually shrink. Over millions or billions of years, the two neutron stars spiral closer and closer together. When they finally merge, the collision releases an enormous burst of gravitational waves, a signal that can be detected by instruments like LIGO and Virgo. The first such detection, made in 2017, confirmed that neutron star mergers produce gravitational waves and also generate short gamma-ray bursts and create heavy elements like gold and platinum. Looking beyond individual stars and binary systems, we can consider stars in the context of the galaxies. Our Milky Way galaxy contains between 200 billion and 400 billion stars. These stars are not evenly distributed. Most are found in the galactic disk, a flattened structure where spiral arms of young, hot stars trace patterns of ongoing star formation. The central bulge contains older, cooler stars packed more densely together. Surrounding the galaxy is a halo containing ancient globular clusters, dense balls of hundreds of thousands of stars that formed when the universe was young. Star formation continues in the Milky Way today. Each year, a few new stars are born in molecular clouds scattered throughout the disk. Most of these stars are low-mass red dwarfs, but occasionally, massive stars form in giant star-forming regions, like the Orion Nebula, a stellar nursery visible to the naked eye as a fuzzy patch in the sword of Orion. The Orion Nebula is about 24 light-years across and contains enough gas to form thousands of stars. Within it, astronomers have identified young stars just a few 100,000 years old, still surrounded by disks of material that may one day form planets. The total number of stars in the observable universe is staggering. Astronomers estimate there are about 200 billion to 2 trillion galaxies in the observable universe, each containing tens of millions to trillions of stars. Taking a conservative estimate of 100 billion galaxies with 100 billion stars each, that gives us 10 sextillion stars. That it's a 1 followed by 23 zeros. If you tried to count them at a rate of 1 per second, it would take you more than 300 trillion years, far longer than the current age of the universe. Each of those stars is a sun, potentially with its own system of planets. Around many nearby sun-like stars, astronomers have detected planets. Some are gas giants, larger than Jupiter. Others are rocky worlds not much larger than Earth. A few orbit in the habitable zone, the region where temperatures are right for liquid water to exist on a planet's surface. The universe may be teeming with planets, and on some of those planets, conditions may be right for life. When you look at stars, you're also looking back in time. Light travels at a finite speed, about 300,000 kilometers per second. The light from the sun takes about 8 minutes to reach Earth, so when you see the sun, you are seeing it as it was 8 minutes ago. The nearest star beyond the sun, Proxima Centauri, is about 4.2 light-years away. When you look at Proxima Centauri, you see light that left the star 4.2 years ago. Many of the bright stars in familiar constellations are tens or hundreds of light-years away. Betelgeuse is about 550 light-years distant, so the light we see from it tonight left the star in the late 1400s, around the time Columbus sailed to the Americas. Some stars are so far away that their light has been traveling toward us for millions or billions of years. When we look at distant galaxies through powerful telescopes, we see them not as they are now, but as they were in the distant past. We see stars that formed when the universe was young, stars that may have already died, their light only now reaching us across the vast emptiness of space. Stars are engines of creation. In their cores, simple hydrogen fuses into helium, helium into carbon and oxygen, and in the most massive stars, fusion continues all the way up to iron. These elements, forged in stellar furnaces, are essential for everything we know. Carbon forms the backbone of organic molecules. Oxygen is critical for water and respiration. Silicon makes up rocks and planets. Iron cores give planets like Earth their magnetic fields. And the heavier elements, gold, uranium, lead, and countless others, were created in the explosive deaths of massive stars and scattered into space by supernovae. Our solar system formed from such enriched material. About 4.6 billion years ago, a molecular cloud containing the remnants of many earlier generations of stars began to collapse. That cloud contained not just hydrogen and helium, but also carbon, nitrogen, oxygen, silicon, iron, and trace amounts of nearly every element in the periodic table. When the sun ignited at the center of this collapsing cloud, the remaining material formed a disk around it. In that disk, dust grains stuck together, growing into pebbles, then rocks, then planetesimals, and eventually into the planets we know today. Earth itself is made from star stuff. Every atom in your body a relic of stellar processes that played out billions of years ago. When you look up at the night sky and see the Milky Way stretching across the darkness, you're seeing the combined light of billions of stars in the disk of our galaxy. Each one is unique, with its own mass, its own temperature, its own age, and its own eventual fate. Some of the stars you see are just being born. Protostars wrapped in cocoons of dust, glowing in infrared as they slowly contract. Others are in the prime of life. Stable main-sequence stars fusing hydrogen into helium, shining steadily as they have for billions of years. A few are in their death throes, red giants swelling and pulsating, or massive stars on the verge of supernova explosions. And some of the points of light you see are not stars at all, but white dwarfs, neutron stars, and perhaps even light from material falling into black holes, the final remnants of stars that once shone brightly. The study of stars has come remarkably far in just a century. 100 years ago, astronomers didn't fully understand what made stars shine. The source of the sun's energy was a mystery. It was known that chemical burning couldn't sustain the sun for more than a few thousand years, and gravitational contraction couldn't keep it shining for more than a few tens of millions of years. Yet geological evidence suggested the Earth was far older than that. The solution, nuclear fusion, wasn't understood until quantum mechanics provided the framework in the 1920s and 1930s. Even then, the details of stellar evolution, the life cycles of stars, remained largely theoretical until observations began to confirm the predictions. Today, we can peer into stellar nurseries with infrared and radio telescopes, watching as protostars form from collapsing clouds. We can observe main-sequence stars across the galaxy and in neighboring galaxies, measuring their masses, temperatures, and compositions. We've studied red giants and supergiants, watched supernovae explode and detected the afterglows of gamma-ray bursts from the most distant reaches of the universe. We found thousands of pulsars, measured their masses with incredible precision, and used them as cosmic clocks. We've detected gravitational waves from merging neutron stars and black holes, confirming predictions made a century ago and opening a new window onto the universe. We've also come to understand that stars are not eternal. Every star, no matter how massive or how faint, will eventually exhaust its fuel and die. The universe itself is aging. The molecular clouds that give birth to stars contain material recycled from earlier generations of stars, enriched with heavier elements. But each cycle of star formation locks some material into long-lived stars and stellar remnants. Over trillions of years, star formation will gradually decline as the available gas is used up or locked away. Eventually, the last stars will form, shine for their allotted time, and fade. Red dwarfs, the smallest and longest-lived stars, will be the last to go, burning dimly for tens of trillions of years before they finally exhaust their fuel. But that far future is unimaginably distant. For now, stars continue to be born, to live, and to die in an ongoing cosmic cycle. Each star is a temporary structure, a localized decrease in entropy, a brief flash of order and energy in a universe slowly winding down toward equilibrium. Yet, in that brief flash, measured on cosmic timescales, stars create the elements, illuminate the darkness, and make possible the existence of planets, life, and consciousness. As you drift toward sleep tonight, imagine yourself floating in space, far from Earth, far from the sun, surrounded by the darkness between stars. In every direction, points of light pierce the void. Some are nearby, bright and clear, their colors distinct. Others are distant, faint smudges barely visible against the background. You are surrounded by hundreds of billions of stars, each one a furnace where hydrogen becomes helium, where light and energy pour outward, where the building blocks of worlds and life are forged in nuclear fire. You are part of this. The atoms in your body, the calcium in your bones, the iron in your blood, the oxygen you breathe were created in stars. You are made of stardust in the most literal sense. When ancient stars exhausted their fuel and exploded, they scattered these elements into space, where they drifted for millions or billions of years before gravity pulled them together into new clouds, new stars, and new planets. One of those planets was Earth. And here you are, a pattern of organized matter, a living, thinking being made from the ashes of dead stars, looking up at the night sky and wondering about your place in the cosmos. The stars are still shining. They will continue to shine long after we are gone. But in this moment, on this night, they shine for you. Their light has traveled for years, decades, centuries, or millennia to reach your eyes. When you see starlight, you are catching photons that began their journey before you were born, perhaps before your grandparents were born, perhaps even before recorded history began. those photons traveled through the vacuum of space, passed through Earth's atmosphere, and ended their journey by striking the retina of your eye, triggering a cascade of chemical reactions that your brain interprets as light. This connection to the stars is real. It is not metaphorical or symbolic. You are literally connected to stars by the atoms in your body and by the light entering your eyes. The same physical laws that govern the fusion in a star's core also govern the chemistry of your cells. The same gravity that holds a star together also keeps you anchored to Earth. The same electromagnetic forces that make stars shine also bind the molecules of your body together. You and the stars are part of the same universe, subject to the same laws, made from the same fundamental particles. As the night deepens and your mind settles into rest, let the stars fade gently from your awareness. You've traveled far tonight. From the cold darkness of molecular clouds to the searing heat of stellar cores. From the explosive violence of supernovae to the strange, dense surfaces of neutron stars. You've seen stars being born and stars dying, stars alone and stars in pairs, stars in our galaxy and stars scattered across the universe. You've learned that stars are not eternal, that they change and evolve, that they create the elements essential for life, and that their light connects us to the distant past. If you enjoyed this peaceful journey through the cosmos, I invite you to like, subscribe, or share your thoughts below. Your support helps this channel continue creating these gentle explorations of science, one sleepy topic at a time. But for now, let all of this knowledge drift away. Let the facts and figures dissolve into a soft, comfortable haze. Let your breathing slow. Let your muscles relax. Let your thoughts become quiet and formless. The stars are still there, shining in the darkness, and they will be there tomorrow night and every night after. But tonight, you can rest. You can let go. You can settle into the comfort of your bed and allow sleep to carry you away, knowing that out there, in the vast darkness of space, billions of stars continue their patient work of fusing hydrogen into helium, of shining steadily through the ages, of creating the elements that make life possible. You are part of their story, and their light, ancient and patient, will still be falling on Earth when you wake. Good night, sleep well, and may your dreams be filled with starlight.